Okay, here we're in chapter 5 on accumulating change, limits of sums and the definite integral. This is section 5.6 on the definite integral algebraically. So how do we develop this definite integral? So for any antiderivative f, capital, of a continuous function little f from a to b, we can say, okay, well, the integral from a to x of f of t dt is equal to f of x plus c. And then when x is equal to a, our accumulation function is basically equal to 0 because when we plug all that in, what we're going to get is f of a minus or plus c equals 0. So c equals a negative f of a. And so if we plug that into this function, then we get f of x minus f of a. Now, what if we wanted to go from a to b, which is the definite integral? Then we plug in a to b, and so instead of x, it's b, and so the integral from a to b of f of t dt is f of b minus f of a, okay? So basically, it doesn't matter what value of c is used in calculating a definite integral. So any specific antiderivative or even the general antiderivative function can be used. And so this is now up to our fundamental theorem of calculus part 2. So calculating the definite integral. So basically, if we have f as a continuous function from a to b and f is any antiderivative of f, then the integral from a to b of f of x dx is f of b minus f of a. It's the definite integral from f from a to b. Now that is the integral from a to b of f of x dx is equal to our limit again of n going to infinity of I from 1 to n, the sum of f of xi delta x, which is all those tables we looked at and we kind of skipped and we went straight from this to this. And so that's f of b minus f of a, where the input interval a less than or equal to x less than or equal to b is divided into n subintervals of width delta x. And an alternative form is when we after we take our integral, we can say, well, that's equal to f of x, and we're going to go from b to a. So we're going to take f of b minus f of a. And I've done that in another video as well, I believe. All right, so let's say we have marginal product. Again, what is that? Well, that's the derivative. So, if we have P is equal to our production or product, if we want to call it that, so it's kind of the same word, then P prime is our marginal product. Okay, so that's back to, again, what we've talked about before a long time ago in derivatives. So a computer technology developer has determined that its production capability increases at a rate of change according to the following model. P prime of k is equal to 0.15 times 1.08 to the k 100 servers per $1,000, where k is capital investment measured in $1,000, and k is between 5 and 25. We're supposed to write a model for production. Well, if we've got marginal product and we need to get to production, guess what? We're going to take the antiderivative. And so that's part A. And then B, how many more servers can be produced when 25,000 instead of 5,000 invested? Well, then we're going to do our integral, and we're going to go from 5,000 to 25,000. And then illustrate the answer from part B as a region bounded by the graph. So then we're going to kind of draw a graph and show where it is. Now again, the constant term in antiderivative does not affect the definite integral calculations. So when calculating change in a quantity, calculating the constant and antiderivative is not necessary, which is nice. So what do we do? Well, we're going to take the integral of this. So if we do that, it's going to be 0.15 times 1.08 to the k over ln of 1.08, and then plus our c, 100 servers. Okay, so that's our general antiderivative. Now they want us to find the definite integral, and they wanted it between 5,000 and 25,000. So remember, it's in thousands of dollars, so 5 and 25 is all we need to do of the integral of our original pk function. And so basically, we're going to plug in 5 and 25 into this. So what we could have done is, and we could have said, okay, well, if this was going down here, what we're going to do is we're going to evaluate that from 5 to 25, kind of like it shows here. And so basically we're plugging that here and we're going there and we plug it into our calculator and we get that that's going to be equal to 10.4800 servers. Okay, so that's going to be our value there. And again, all we did was we took our integral and evaluated, f of 25 minus f of 5, and we got 10.4800 servers. Then what we do is we plot it, and we plot basically our p of k function, our p prime k. And what happens is what's going to be under our integral sign here is we're going to go from 5 to 25,000, and that area under the curve is going to be the area we just found, 10.4800 servers. Okay, so that's going to be how we get our plot. All right, so let's stop there and we'll come back with more.